Thank you for introduction. And I'm very happy to join this nice meeting and to have an opportunity to make a presentation about our project that is TAO 6.5 meter telescope project and its instrument MIMIZUKU. Okay, I'd like to start my presentation with my introduction. My name is Takashi Miyata, a professor of Institute of Astronomy at the University of Tokyo. And actually, I have been working for 25 years on meteorite astronomy, especially for the instrumentation of the ground-based meteorite instruments. And I was a member of Subaru Comics development team. So I'm a little bit sad because the comics retired in this year. And anyway, I'm working on the TAO project, and actually I'm a project manager of the TAO project and PI of its meteorite instrument called MIMIZUKU. And 20 years go by since we started meteorite observation with using 8 or 10 meter class telescopes. And it was, of course, very exciting, and it was very fruitful, I think. But it's time to go into the next step. So we need to consider what's next. And of course, one promising way of the next ground-based meteorite observation is higher sensitivity or higher angular resolution. And it is, of course, very good, but it needs an extremely large aperture. So this, this direction should be pursued by 30 meter class telescope project. For example, MICHI or METIS. And I think there are the other directions of the future meteorite ground-based observation. One direction is going longer wavelengths. Traditionally, in my experience, Q-band observations are not easy, even at the Mauna Kea site. And of course, we don't have any access beyond 25 micron from the ground. So many science cases still remain in this wavelength range. One example is the spatial structure of the disk, planetary disks or the debris disks. Of course, the longer wavelengths traces, of course, the lower temperature regions. So we can investigate the detailed structure of this such kind of disks, especially the outer region or midplane of the disks. This is very important point. And in addition, there are many dust features in these wavelengths, 20 micron or 30 micron. And this is an example of the feature crystalline silicate. And this is a laboratory measurement. And you can see some interesting feature around 20 or 30 micron. And these features are very important to identify or investigate the component of the crystallized silicate. So this should be investigated. This is one direction, I think. And the other important direction is the time domain observation. And of course, time domain observation is one of the hottest topics in modern observational astronomy. And there are many projects in optical or near-infrared wavelength range. But unfortunately, mid-infrared wavelength time domain observation is unexplored because of the difficulty of the monitoring observation in these wavelengths. On the contrary, there are many mid-infrared variables in the sky. Of course, AGB stars are variable stars, and some YSOs show very strong variability like FU Orionis phenomenon or something. And AGNs are also variable object. So we need to carry out this kind of object with a monitoring observation. And for example, we can study the dust forming process in various objects by the meteorite monitoring observation. This is an example of the time version of OHR star, kind of AGB star, and you can see the clear variation and the spectra. And dusty nova is another important object to be studied. This is an example of the dusty nova V128 score taken by Sakon-san. And these objects are very important for the dust supply in the universe, so we need to investigate these objects with the monitoring observation. In addition, of course, for follow-up of some transient objects are very interesting. So, we want to go to longer wavelengths, and we want to carry out monitoring observation. To go to longer wavelengths, we need to go higher side. And to carry out monitoring observation, sufficient and flexible observing time is needed. So that is why we are promoting the University of Tokyo Atacama Observatory, that is TAO. Okay. And this is a brief overview of TAO project. TAO is a project to build a 6.5 meter infrared telescope at the world's highest site in Atacama. This is the schematics of the Atacama area, and here is Pamparabola Plateau. This is very famous as Alma site. And the altitude of this plateau is about 5,000 meters less. And there are some peaks on the plateau, and one peak is called Chajnantor. And we will install a relatively big telescope for the infrared observation. That is the TAO project. And the altitude is 5,640 meters. And this is the world's highest astronomical observing site. And it is certificated by the Guinness World Record, like this. And thanks to this very extremely high altitude and dry weather condition, we can use some new atmospheric window. So we can carry out frontier sciences from cosmology to solar system with this telescope. And TAO is a university telescope, and it is promoted by the University of Tokyo. And so we can focus on educational and exploratory observations. That is another important point of the TAO project. Okay, this is about the atmospheric transmittance at the TAO site. Blue shows the TAO site, and green shows the SPAL site, and red shows the VLT site. And you can see the beta transmittance at short L-band wavelengths, especially 3 micron region, and M-band and Q-band. And the new window appear around 30 micron, like this. And so we believe this TAO site is the best site for the mid-range infrared astronomy. Okay, so but you may think, is the 30 micron region really usable for scientific observation? Because this is actually not so good window. So we need to evaluate this window. So we made some evaluation test with mini-TAO and max 38. Mini-TAO is a 1 meter telescope. That was a pathfinder of the TAO 6.5 meter telescope. It was installed at the summit of Chajnantor and operated from 2009 to 2013. And it equips a multi-infrared camera called Max 38. It uses a silicon antimonade detector, and we can observe 30 micron wavelength range. And as a result, we successfully obtained some images of bright objects at 30 to 38 micron. And this was the first trial to observe the 30 micron wavelength range from the ground, I think. And so we think that this wavelength region is usable for scientific observation. Okay, and this is about the observing time of TAO. And TAO is, as already mentioned, the university telescope and built and operated by the University of Tokyo. And we have a flexibility to allocation of the time. And TAO have has a limited number of instruments. We have two facility instruments, that is MIMIZUKU and SWIMS. SWIMS is a wide field imager working on in the near infrared wavelength range. It has imaging capability and most spectroscopic capabilities. And one more instrument for fast light is called NICE, and that is also a near infrared spectrometer. And anyway, we only have three instruments, and so instrument in use can be switched by just rotating the telescope surgery. These instruments are attached on the non-Smith focus of the telescope, and we can change the instrument, just rotating telescope surgery. So we can exchange the instrument during one night observation. So this kind of flexibility is very important to carry out the time domain observation. Okay, so this is about the MIMIZUKU. And the MIMIZUKU is the facility instrument for the TAO 6.5 meter telescope. And the specification of MIMIZUKU is summarized here, but maybe it's too small, so sorry. And this is a photo of the MIMIZUKU. And yeah, for more detail, please visit our website shown here. And this is a development team of MIMIZUKU. And actually, the development team is very small, and it is about 10 or less members, including a graduate student. Okay. So I will summarize the uniqueness of advantages of MIMIZUKU. MIMIZUKU has some very unique capability against the current meteorological instrument. One uniqueness is wide wavelength coverage. MIMIZUKU covers 2 to 38 micron wavelength range, and we can achieve high spatial resolution. Of course, it is not extremely high spatial resolution because we only have a 6.5 meter aperture, but we can achieve the diffraction limited spatial resolution. It is important to, especially for the longer wavelengths. And highly accurate photometry can be conducted by using MIMIZUKU. For this purpose, we have developed a new device called field stacker. I will describe later in my presentation. This. Okay, and wide wavelength of 2 to 38 micron is covered by 3 channels. And the near infrared channel equips the Hawaii 1 RZ array. It has a format of 1K by 1K manufactured by Teledyne. It is a 5.3 micron cutoff. And the meteorite region is covered by Aquarius 6 to 26 micron, and it is manufactured by Raytheon. And the longest wavelength, 30 micron wavelength range, is covered by silicon antimonite detector. This is not so large format. It is 128 by 128, manufactured by DRS. In addition, to achieve this wide field coverage, we employ the refractive optics as cold optics, and the mesh filter used as a bandpass filter at 30 micron wavelength. Mesh filters have been developed by ourselves, and observing channel can be easily switched. We cannot carry out simultaneous observation on these 3 channels, but we can switch very easily within 10 minutes or something. Okay, this is about observing mode and sensitivity. And MIMIZUKU has imaging and low resolution long slit spectroscopic capability, and some medium band filter for imaging installed like this. And the spectroscopic mode resolution is 100 or 600 or something. Actually, sensitivity is not so high. It is comparable or less worse than the Subaru Comics or other instruments. Sorry. And this is about the diffraction. Sorry. the spatial resolution, and we can achieve the diffraction limited spatial resolution at the wavelength longer than 8 micron. And this is wavelength and spatial resolution, and rate is MIMIZUKU. And you can see the MIMIZUKU has the highest spatial resolution at the 30 micron wavelength range. That is about 1.2 arcsecond at 30 micron. This is a very big advantage of the MIMIZUKU instrument. Okay, and this is about the photometry or monitoring. And in monitoring observation, time fluctuation of the atmospheric transmittance is very big problem and very critical for accurate monitoring. And in optical or near infrared wavelength range, differential photometric method is applied to cancel out the time variation of the atmospheric transmittance. But in many cases in mid-infrared wavelength range, there are no stars around the observing target like this. This is a schematics of the mid-infrared sky, and there are very limited number of bright objects, and the field of view of camera is not so large, so we can obtain only one target at once. But if we can take two discrete or more discrete fields simultaneously like this, we can apply differential photometric methods for the mid-infrared observation. That is the basic idea, basic concept of the field stacker. Field stacker is an opto-mechanical system mounted between the telescope and the MIMIZUKU optics. And it consists of two movable pickup mirrors, here, and one combining mirror here. And it picks up two fields from the telescope field of view. And it enables us to carry out simultaneous observation of two or more stars. And we think we can dramatically improve the monitoring accuracy or reliability. Of course, field stacker is very useful for monitoring observation, but it has also very useful for other mid-infrared observation. One is spectroscopy in hazy wavelength region. And for example, Q band or LM band accurate or reliable cancelling of the sky absorption is very difficult generally. But field stacker enables to get a reference star spectrum simultaneously like this. We have a spectroscopic mode with using a QRISM, so we can take the two spectra simultaneously. So this is very powerful tool to carry out the spectroscopic observation in these hazy wavelength range. Okay, and this is an example of the science cases, and that is water-related materials or hydrated minerals in solar systems. This kind of the hydrated minerals are very important to understand the origin of Earth's water or the thermal history of the solar nebula. And it shows a very strong absorption feature at 2.7 micron. And recently, this kind of absorption feature detected in some asteroids by Akari spectroscopic observation. That is an example of the absorption feature. But unfortunately, this feature is located between the K band and L band. So, so it is very difficult to observe this wavelength range from the ground, but TAO can observe it. And this is the atmospheric transmittance between K and L band. And you can see the very narrow but significant window at 2.73 micron or something. And if we can use this window, we can put the 1 point between the K and L band in the asteroid spectra. That is very important to identify the absorption feature. So we have a plan to make some survey observation of this kind of asteroids. Okay, and another merit of the field stacker is the improvement of the imaging performance and reliability. And in some cases, objects are marginally resolved, may experience. And we wondered, is this real extension or just seeing effect? It is very difficult to judge. But FS can obtain a reference PSF data simultaneously, so we can improve the reliability. And this is burst mode image, burst mode video of 2 stars obtained by MIMIZUKU plus field tracker at the Subaru telescope. And this is completely different star, but this is very synchronized. It is very interesting. And you can conduct the shift standard or lucky imaging method. You can apply the standard or lucky imaging method based on this reference PSF. This is also very good for imaging observation. Okay. So,
5 minutes?
Okay.
Or less, actually, yeah.
And this is about the current status of the TAO telescope. And most of the telescope parts, including mirror, mount, and enclosure, already fabricated and tested in Japan, US. And the primary mirror was fabricated in the mirror lab of the University of Arizona. And the telescope mount and the enclosure was fabricated in Japan. It was tested. And site access road almost completed, and the summit was successfully leveled. That is the situation as of March 2020. But the worldwide pandemic of COVID-19 made a strong impact on our project course. And COVID-19 was spread in Chile too. And the number of cases of deaths strongly increased between February to June. So on March, we decided to stop all site work, and all workers left the site, and the Japanese staff went back to Japan. All activity was stopped. That was very tough situation. But fortunately, around August, the situation in Chile getting better. It decreased, the number of cases decreases like this. So we have restarted the site work on this September. So this is a photo of worker under the new normal. They wear the masks on there. And if everything goes well from now on, telescope first light is expected in early 2022. Okay, and this is about the MIMIZUKU. MIMIZUKU is also the final phase of the development. And basically, mid-infrared S channel is ready for observation. And we made some engineering observations at the Subaru telescope on 2018. And the basic function and the performance was successfully confirmed. And the result of this engineering observation will be reported by Kamizuka-san tomorrow morning. And achieved performance of field stacker will be given in Michifujitsu's talk just after my presentation. Okay, and after the engineering run, MIMIZUKU came back from Hawaii to Japan to make some improvement. And one of the most important development item is cold chopper. The TAO telescope doesn't have a chopping secondary, so we need to develop a cold chopper system in the inside of the instrument, like this. So we are now developing a cold chopping system, and this cold chopper system will be installed in MIMIZUKU for optics. That is called optics, and the operation temperature is 30 Kelvin. And it has a 2-axis motion with 2 coil actuator. This is a schematic of the cold chopping system, and this is a movie with the room temperature. And this is chopping system is now under development in collaboration with Honda-san and some expert of system control. And this is a kind of prototype of the cold chopper of TMT Michi.
1 minute, please.
Oh, okay. Okay, we also need to improve the detector operation, prepare operation reduction software before going to Chile. And after those improvements, MIMIZUKU will be shipped in 2021, next year, and the science operation will start in late 2022, hopefully. Okay, this is a summary of my talk. TAO is a 6.5 meter telescope project at the highest, that is means the best site of mid-Earth astronomy. MIMIZUKU has very unique capabilities, wide wavelength coverage, high spatial resolution, and high accurate monitoring. And they are now final phase of the development, and hopefully we would like to make a start a scientific observation in late 2022. That's all. Thank you very much for your attention.
Thank you very much. This is indeed very interesting, this new instrument, yeah, and the telescope. So I forgot to mention actually before the talk that all questions should be posted to the instruments channel, but I see already some questions are there, so it didn't completely fail. I will read the first question, but I think it was already answered in the talk actually in one of the figures. So what is the typical PWV for the TAO site? So maybe you...
Yes. Typical PWV is about 0.5 or 0.6 millimeter. And this is based on the calculation of the, assuming the PWV is 0.4 millimeter.
Okay. Also another question by Roy. Are the field stacker optics in the cold?
No, this is warm optics. So.
Okay. Another question, will TAO be operated in classical or Q scheduled mode?
Not yet decided, but at least the first phase we will start with classical mode. But the site is very tough condition, so I think we need to develop some remote observing mode, at least.
Okay, still we have a couple of more questions and then we have still time. Okay, so are you affected by the Aquarius detector Elfin noise, or do you have an effective way of canceling this?
Not here, actually not yet tested detail, but maybe the Elfin has caused effect on our detector, so we need to make some improvement of the operation of detector, Aquarius detector. Not yet done.
Okay, and I think one more question. No, actually, it's a question for Olivier. Okay, so I think I hope I didn't miss anyone's question. So in case, basically, if you have more questions, so please check the Slack channel and continue the discussion there.
Nadine, there is one more question by Bernhard that I think is worth asking in the public.
Oh yeah, okay, yeah, sorry, I missed it. Okay, so it is great to see an alternative to bigger is better. The only question is whether observing time is publicly accessible. So is it available to the public?
Okay, and the TAO observing time, half of that observing time is used for the project time. That is the project of the University of Tokyo, and 40% is used for open use. But now it is limited in the Japanese community. Sorry, and the 10% is Chilean time. Of course, collaboration is very welcome to us.